Thanks, everyone. My name's Dunk. I'm going to try and talk to you today. I'll be very honest with you. All public speaking is not my forte. As I was telling somebody earlier, I'm usually locked in a dark box with maybe one or two people, and that's about enough for me. So if you'll bear with me as we step through this, that'd be lovely. If I do end up racing off talking really fast at any point, somebody just tell me. Okay, I do apologise in advance. So quick overview of what I'm going to attempt to talk about today. Flight simulators, in essence, going from the aviation industry, designing power management systems on commercial and military aircraft, into what I do now, which is both full-size and desktop flight simulator development. So give you a little bit of an overview of that and a little bit of an overview about the history and the career path and how I got to where I am today. Talk a little bit about some of the technical challenges and how it works. Hopefully, if the stars align, because we're all relatively familiar with computers in here, if everything comes together, I do potentially have a little demo towards the end if I manage to talk quickly and we have a bit left over time. That might be an opportunity to take a 320 for a bit of a spin, if that sounds reasonable. If anyone's got any questions as we step through this for me, then please feel free, just fire them out. Won't be a bother at all. Okay. Right. That worked. That's always a good start. So what got me here? I came through secondary school without too much of a plan, which I don't think is too uncommon in this day and age. Decided that university was not really for me and went straight into a degree apprenticeship with General Electric. I don't know if anyone's familiar with the degree apprenticeship. But I was in the second year they'd ever been run. Pretty fantastic way to do it. They packed me off to university 1 day a week and I had to work for 4. It was a balancing act, but we made it work. The really cool thing about that from my point of view was that I was hands-on in the workforce. I was designing and engineering on parts that were going on aircraft at that point. I started out that journey heading down the software route, which is where we come to today. But actually halfway through that kind of apprenticeship journey for me, I switched more to a systems role. And that will become a little bit more evident in a second. So the course I was on at General Electric was 5 years long. I did both a foundation degree in aerospace computer systems and then a bachelor's in computer systems integration, both at UE. Got to work on some really cool stuff. On my roll off of that, I went into the workforce at GE properly, and I was responsible for the worldwide fleet, the Boeing 777, and the electrical load management system on that, which is the boxes that sit under the cockpit floor that distribute all the power to the seatback TVs and all that kind of good stuff. Takes the power off the engines, chucks it around the aircraft. Pretty interesting bit of kit. One of the key roles I was doing there was both a software and a systems role. So we were both designing and recertifying units to go onto new types of aircraft and new configurations of aircraft, but also doing in-service support. So it blew my mind at the time, I won't lie to you, but they actually gave me a 777 for a week. So I sat down on the pan at Cardiff with my own 777 that I had signed for from BA, and we were trying desperately to break it. And that was very much all three disciplines investigation with a team of 2 of us. So it was a systems, it was a software, and it was a hardware type event. We're chasing down why the ram air turbine, which is the backup emergency power source for the aircraft when it's in flight, was popping down whilst they were turning around the airfield. Never a good plan. This was due to in the height of COVID, and there were some operational factors that kind of played into that at the time. So that was one of the highlights. The other product that I was heavily involved in at the time was Gulfstream business jets. So I did a lot of the qualification testing and delivery testing of the power management system for that as well, which was a 5-unit system. All 5 units went on each aircraft, and pretty nifty. Did away with circuit breakers. We all know and love circuit breakers. We've got them all in the boxes in the houses and all that kind of good stuff. On an aircraft, usually they sit behind the captain, the first officer's seat, and they make up from 750 to 1,000 kilos of weight when you throw in all the wiring and all the actuation, all this kind of good stuff. Part of this next generation power system that we were involved in was we did away with all that and turned it into contactors, silicon carbide contactors in a little box like that. 3 of those, whole aircraft job done. So there's some really cool technologies involved. That made up 12 years, end to end, which was a really cool way. to do it. Whilst I was still at GE, I started getting heavily involved in flight simulators. I'd always had an interest in flight since I was a kid. Flight simulators was one of those things as a teenager that I kind of fell into. And it kind of snowballed from there, and ended up being asked to go and have a look at a full-size flight simulator in London that was very, very broken. And we are talking spectacularly broken. They'd been trying for 3 months to fix this thing, and it wasn't going very well. I turned up one afternoon, 3 hours later, they had a working flight sim. And that's the start. So I kicked around with doing contract maintenance work on flight simulators for a good number of years, and then had the opportunity to kind of do my own thing with it. So we started Velocity, my brother, my dad, and myself, in 2015. I wrote that. I'm pretty sure that's right. The only way I could remember was to check the incorporation documents, and I didn't have time. So we started Velocity in 2015 with the intent to provide non-certified, realistic flight experiences and flight training to both consumer, general public, and to commercial crew. And here we are, a good number of years later, still doing it. So we're doing something semi-okay. Off the back of that, I'm not somebody who likes to do not a lot. I don't do well just sat around doing nothing. So during COVID, I started working for a company called FS Labs, or Flight Sim Labs, and they provide A320 series aircraft to the desktop consumer market, as well as full-size simulator environments. I joined them originally doing C#, and it's all kind of morphed into something a little bit more, which we'll run into in a second. So yeah, and that's just a little shot from one of my flying escapades. Nothing like a little bit of cloud surfing. So, touched on some of this briefly. What keeps me out of trouble? It's something that needs to be done. But the stuff with Velocity, as I said, we mainly do commercial flight training, but on top of that, we do general public experience work. We also do a lot of charity work. My usual explanation to people is we do the first two to make sure we can do the last. We do a lot of work with the Great Western Air Ambulance, as well as a charity called Flight Help, which is local to Gloucester, who specialise in doing kind of experience and support days for terminally ill children and young adults. So something that's quite close to my heart. So we and my family. So that's one of our big charity outputs, if that makes sense. FS Labs, as I said, A320 fixed based and desktop simulators, and we'll dive into the fidelity of that a little bit. The other thing that I really quite enjoy doing is photography, and just to bore you towards the end of this, there's some of the photos there that I've won awards for, so we'll show you those as well. I'm going to keep checking this because it's got my notes on it, and I have a brain like a sieve, so you'll have to forgive me, I'm afraid. Yeah, I've kind of talked about this already, but there you go. I'll tell you a little bit how we came into the 7.3 that we have, how we built it, what kind of architecture we're looking at, how it all kind of works, and some of the challenges that go with it. Everyone looks at a lot of people that come into work for me look at a flight simulator like ours and they go, I really want one. Can you build me one for the garage? And I'm like, yes, 100% can do. That is a service that we provide. The biggest problem, however, is 3 months down the line when we start to get into the how do you maintain it? That is where the real trouble lies. Desktop sims seems like something really straightforward. Kind of got from David that a lot of people in here are involved in IT, so we all know what users are like, and we all know what users' computers are like. So it is what I like to term the Wild West. One of the other charity things that we do with the 7.3 is we do an event called World Flight. I've got a little section on it towards the end because it highlights some of the ways that the software engineering has to adapt very rapidly. And then, yeah, we're going to talk about architecture and how everything plugs together as we step through. So one of the things that I hear quite a lot, and if you've had any kind of exposure to flight simulators on the Xbox or on the computer or in any kind of way, is realism. Now, realism is a very subjective thing, and it comes in three key forms. Flight model, how the aircraft flies. Okay, does it handle like the aircraft that you think it should? I.e., do you have a little 1.5 ton Cessna okay, that is handling like a 250-ton 747. That's not realism in my eyes, and in many eyes. The next one is going to be systems. So how it works, aircraft are not simple things, as I'm sure we're all aware. There are many subsystems in there talking, and there are a couple of different ways you can approach that level of realism. And we'll touch on that shortly. And operational realism. So you've got the systems, you've got the flight model, you've got those both absolutely nailed. How are you going to use it? And that's where a lot of the extra bits and bobs come in that we've done relatively well on the 737 and in the 320. Little picture here. So this is, to put this in context a little bit, it looks like we're turning quite steeply. This is what we call a steep turn in the 737. It's something that's kind of bread and butter for our pilot training work that we do before crews go to interview for an airline. So that is a 60-degree left-hand turn. Not something you'd ever see on the line, okay? On the line, you're going to get screened and shouted at by the aircraft by about 33.5 degrees, okay? Anything more than that, it gets very noisy very quick. The idea when you go to interview is you're going to do one of these turns for 360 degrees, and you're not going to lose plus or minus 10 feet, okay? When you roll out wings level, you're going to be plus or minus 1 degree in terms of your stated heading, and you're going to be plus or minus 5 knots. So that's the output end of what I term the operational realism. Okay. There we go. So how I class the pyramid, so to speak, of realism when it comes to the engineering side of simulators. Visuals, they sell product. Okay, especially in a desktop environment, they sell product. Flight model, it's going to be the most relatable thing for consumers, whether you're in a full size or a desktop simulator. Most people can, when they're on a flight sim in whatever context, can understand whether or not this feels like a 250-ton aircraft or a 70-ton aircraft. Okay, just like you go from a Nissan Micra to a 5 Series BM, they feel differently. Yeah, very similar for an aircraft. Most people can draw a parallel to that. And then systems and ops, as we talked about. I would call systems and ops the most valuable, as you've probably gathered from what I've said already, because that's where, if you get that bit right, everything else, apart from maybe the visuals, will follow, and you'll have a very well. Cool. So, flight simulators, there's 2 aircraft we're going to talk about today. I've steamed ahead with lots of plane names, so apologies if we're not overly familiar with aviation in the room. The 2 we're really going to look at today, it's going to be the 737-800, which is a Boeing produced, so it's produced in Seattle, a single aisle commercial airliner. In the max config, it's going to seat 186 people. It'll fly for about 6 and a bit hours at maximum. That's your kind of limits of it. It's going to take you to Egypt and back. You're thinking Ryanair, TUI, Jet2, okay? The second plane, for me, it's the desktop environment that we develop, is going to be the A321neo, which stands for the new engine option, and very similar again to the 737 in terms of class. The difference is that's more of a kind of an EasyJet and BA plane. Okay. So, I wasn't sure if this would be of interest. This is from one of my very first planning documents when we moved our sim from its former home to our new one, which came with a whole host of bits and bobs. But just to give you an idea of the size and scale that a installation like this takes up, the room itself is 5.5 meters by 5.6 and 3.7 high. And we use every inch of that in terms of projectors, screens, the actual cockpit itself, the racking, the computers. Our sim is fixed base. It does not move. Okay. The way aviation training works these days is you do not need full movement in order to achieve the training goals that are set out by the airlines and by the individuals. The other negative for me of full motion sims is they cost a lot of money. Okay. You are looking at, for a certified full motion simulator, £750 an hour. Okay. I'll put this in perspective. I charge our 737 now at 85 an hour. Okay, so cost versus value, fixed based, unless you're doing something that needs full motion, is quite often where it is. we actually took the front end of the aircraft. We pulled it off a aircraft. I actually have the tail number here somewhere. He says it's an ex-United 737-500. I think it was 241 uniform alpha. If anyone wants to double check that with me later, they can do. We took the full cockpit. We pulled out of that what we wanted. Okay, so it wasn't cost effective to ship the whole nose of the 73 home from Arizona. That gets really expensive really quickly. So we pulled out the bits that we wanted. Okay, and the key items for us to give that systems and flight model realism that we talked about at the start was going to be the flight controls and the throttle quadrant. The two items on any aircraft that you're going to use the most. Okay, because when you're flying an aircraft, one hand's usually on the yoke or the side stick, and the other hand's going to be on the throttles. So that sets us apart because no one else in the country has the real pairs of those and uses them in the way that we do. We also took a lot of kind of sub paneling as well for the overhead and various other parts of the cockpit. They're kind of hard to find. So once I had the opportunity to get them all, yeah, happy days. The real problem then became integrating a lot of them. Commercial aircraft mainly use a protocol called ARINC to subsets of the ARINC protocols to communicate. So breaking that out from a panel level into a computer level was a small challenge. So we designed some custom converter boards. So we did TCB engineering on those boards to convert the panel level inputs and outputs over to something that we could handle via USB and some custom drivers. So the other really cool thing we took was the seats. It sounds really basic, I know. We quite often, in the instructing team at work, will quite often do 14 to 16 hour days. It's a lot of time sat in a seat. The really nice thing about the crew seats on the 73 is they're actually really comfy. So that's a nice little added benefit. It also comes with all the height adjustments, so and the lateral adjustments as well. So you can take somebody who is kind of 4'6" and position them so that they can see over the front of the glare shield, which is actually really quite tall on the 73. If you're stood up, it's kind of sat, the lip of the glare shield on the 73 is sat about there. So when you're sat down, if you're kind of anywhere below about 5'2", you have to kind of start playing around with the seat quite a lot to get your head over. In terms of visuals, we actually had a screen custom built for us. We used a slightly different visuals engine to most. It's a system called it's a system from Lockheed Martin. It's called Prepared 3D. It's used all over the world in many different full-size simulator applications, and you can use it at home on your desktop as well. But we use Lockheed Martin Prepared 3D, and then we have 3 4K projectors mounted on a gantry that shoot crossways, as you can see here. So they shoot across each other, and that gives us a 12K screen end to end, which is pretty impressive, especially at sunset, because who doesn't love a sunset, even if it is on a computer? All of our displays are done in C++, so it's GDR rendered, and then we run we use a custom communications protocol. We run a bit of a distributed network on the simulator on the 7.3. There's 8 computers in total, and then basically, so we have a master, which is my kind of access everything machine. We have 2 that handle the core logic. Now, although we've only got the front end of the aircraft, we actually simulate the whole aircraft nose to tail. Okay, so if you do, for instance, okay, we're getting airborne, pop the gear up, and then we start to retract the flaps, but we do so probably a little bit quicker than we should. You will actually get the hydraulic pumps, because of both the gear and the flaps on the 7.3 run hydraulically. You will actually get the hydraulic pumps cavitating, and you'll see that on the overhead with the flashing of the pump lights as they cavitate. So that's the beauty of simulating the whole aircraft nose to tail. You can replicate everything that that aircraft will do in all the situations. So we don't just deal with normal ops. We do a lot of abnormals as well. May that be from Sean the Seagull taking a visit down the engine, to a fuel leak, to a generator off situation or anything like that. That's all stuff that we do day to day. And the simulator behaves just the way the aircraft would. Yeah.
I'm guessing users play a big part in when you're trying to simulate a whole aircraft. They do something.
Yes. Yeah. So you get We only tend to really delve into the abnormals with our commercial crews. So it's a really good way to show whether they've done their homework, whether they've done the prep for the session. But if you get people start to do the wrong procedures for a failure, then things get compounded really quickly. But yeah, the person in the seats, the people in the seats can cause a lot of problems when it comes to this kind of thing.
You have 8 computers running.
Yes.
How many, how many is actually on a real 737?
Now I'm doing maths. So you've got at least 23 in terms of redundancy as well. So, for instance, you've got 2 flight control computers. You've got one on the A side, so on the captain's side, one on the B side, on the first officer's side. And so they will control the FMC, so the flight management computers. And they'll do all your lateral and vertical navigation calculations, basically. So yeah, across all aircraft, there's probably 22 or 23 that I know of.
A lot of processing power.
It's a lot of processing power, but it's also not. Okay, these are not computers that we would have at home. These are not. Aviation tends to lag 20 years or so behind consumer technology. You're only really in the last couple of years starting to see LEDs on aircraft. Okay, something that we all take for granted. Yeah, you're only just starting to see them make it into cockpits and onto the wings for the lighting systems of the external lights of the aircraft. And that's because there is a reluctance to adopt these new technologies before they become proven. And as a rule of thumb, 20 years is about what they would call proven. So these are much lower spec computers than we would associate with what we have in mainstream consumerism today. I just wanted to kind of put it in reference for what we were talking about, to be honest. So this is the cockpit of our 737. As you can see, it's got five crew screens across the center there. It's called the CDS, the crew display system. And then these are our yokes and our throttle quadrant. The yokes and the throttle quadrant actually did 27 years on the aircraft before we got them. So they've seen a good life. We, with a third party partner, refurbished them and then converted them over to where we wanted them to be, both for the next generation spec of 737 and also in terms of getting the data out of them that we needed. Just like a joystick, here's one I bought earlier. We need a way to get the positional information out of the flight controls in the simulator. So in terms of hardware, we used a kind of a combination. So we have a fallback. So there's a Hall effect sensor in there, and there is also a string potentiometer. One of those went pop on me yesterday. That is what we call a 2 out of 10 job, because that requires me to go under the floor. Now, as we can all see, I'm not exactly small. It is a very small space under there, and I'm going to have to put that off for another couple of days because that does not fill me with joy and happiness. Everything in here works. You can literally take the procedures off the jet and do them in here, and vice versa, which is one of the key things that we do. And that's the level at which, both for consumer and for professional flight simulators, that the customer base expects these days. Cool. One of the things I've learned over the years, whatever code you put into this type of environment, you need to make sure it's protected, because we have users. Okay. The gold standard is fast and clean code that is protected. We all know the gold standard rarely works in an actual environment, but some form of that is always useful. Okay. It's amazing how many people will do things that you do not expect, especially when they have a keyboard in front of them, even on an aircraft. Okay. The systems, I've kind of put on here, the cockpit is the last step. Okay. When it comes to any type of full-size simulator, the cockpit is, yes, the thing that everybody sees and goes wow to. But if you don't have the guts behind it, then it's just something that looks relatively pretty, but is essentially non-functional. Okay.
is most of software half the time anyway.
Well, yeah, exactly. So that's where that systems depth from the software comes really into being. It's what gives the product life. Maintainability. I've kind of touched on this already with my broken with my damaged flight controls. However, there are 3 key things that I've learned over the last 10 or so years that really mess with full-size flight simulators. Calibration drift and wear and tear. People are not kind on these. Weirdly enough, flight crew are the worst. Okay, they are used to being given the keys, theoretical keys, to a £60 million aircraft. Okay, and at the end of their flying day, they give the aircraft back and they write in the logbook what they broke. Not even joking. And then it's not their problem anymore. Now, they will take, if you give them something that feels like the real thing, they will treat it with the same context because that's what they do at work. Okay, and that's one of the things we saw quite early on was we'd have commercial flight crew come in and they would beat it up. Didn't help my blood pressure stay under control, I can tell you that. So calibration drift and wear and tear, they both kind of tie together because one comes from the other. Noisy sensors, again, the movements and bits and bobs. One of the things that I haven't yet touched on that we have is quite an interesting sound system and a way that we provide haptic feedback through the floor and through the seats. It's very nifty. It kind of bridges the gap between that fixed space, nothing's moving, all you can see is like you can see the window, everything out the window moving, and that's it, to that full motion, you're getting sensations. We kind of bridge that gap. The downside is, if you haven't clinched something down tight enough, it's going to move. I won't tell you how many times I've done that. And then the bane of my life in its entirety is USB. Wonderful bits of kit, but we are slowly moving to Ethernet with all of our interface boards and all of our panel heads. We can give the power over Ethernet. We can reliably take the data and it latches nicely. We also don't then have to worry about having the USB connected directly to the computer, which doesn't sound like too much of a drama, but when you've got, I think when we first built the 7.3, it had about 60 USB outputs. Yeah, there's some people in the room who know how horrible that was. So having to have the computers that close before you start running into kind of length of cable issues with those as well. Bear in mind, the overhead is another kind of 2 meters further forward of the front of the simulator. So you add 2 and a bit meters onto the run of the cables straight away. Being able to swap those out for Ethernet boards has been an absolute godsend. The reliability has improved tenfold. So we are slowly eradicating that. But as ever, cost becomes an issue. They are not cheap. They are 4 times the price of a USB interface board. So as and when I can, we rip another couple out. I won't lie to you. This has to be my favorite slide, just for the title. Desktop sims. So when I talk about desktop sims, I'm talking about the ones that we might have at home on the computer and all that kind of good stuff. They are, in my view, the Wild West, because you control, as a developer, you control nothing of the environment, but you have all of the expectation. People expect to have AAA game performance, complete reliability, and to be able to treat the aircraft exactly like they would if they were in a £60 million. It's a really large set of requirements. So you can get it right at one end. So if you've got the absolute beast of the latest and greatest, you're running a 5090 graphics card, an X3D processor, all that kind of good stuff, it works beautifully. But then you've got Joe Bloggs with the hand-me-down laptop, and there's nothing wrong with it because everybody gets into computer gaming in a completely different way, at different points with different budgets. So what may work for Supercam Honduki may not work for Joe and his laptop, and it's trying to find that balance, which can be a challenge. Now, I do all my desktop flight sim development on Microsoft Flight Simulator. So I don't know if anyone's heard of that. Both 20 and 24. Constant updates and limitations in terms of APIs and interfaces are a challenge. And that tailors how you approach the problems. You're getting updates for these game-breaking updates that you can't, that are forced. These updates are shoved down your throat whether you want them or not. You cannot skip them, okay? You start the program and it updates regardless of what you want it to do. So you have very little version control against a moving target. And the biggest impact of that, to be honest, is the amount of time you have to sit there. You know, you get to understand the game's development cycle a little bit. Normally, a Thursday evening about 8 o'clock, they'll drop an update. That means my Discord starts going off at 8:05. And all of a sudden, there's a lot of work for us to do in terms of guaranteeing the compatibility. It sounds something really small, but when you've got a large customer base who all want to be able to use your product on this brand new version of the game within 20 minutes of it being released, that's actually quite a large time draw. It doesn't necessarily equate to the best engineering ever. Yeah, that's probably my favorite point. I stay with it. As with most computer systems, people are the weak link. Whether that be on the support side or how they're using it, doing something completely different to what you expect, or just not being able to explain what they're doing when it comes to trying to fix the problem. So, small comparison. Fixed base simulators, desktop simulators, they're kind of all striving to do the same thing. You want the realism in one way or t'other. I brought some hardware with me today, as I said, just to kind of show some of the advances that the desktop sphere has had in terms of chasing that realism in the comfort of your own home. The fixed-based environments tend to be very controlled. As an owner, as a developer, as an engineer, you have complete control of the situation. You can push your updates when you want them. You can deal with the downtime in a manner that you would like to, and you have a structure around it versus the desktop cycle. So we're chasing the same thing on both sides. They're just not necessarily always coexistent. Next couple of slides are some pictures. I think they're pretty, but there you go. These are pictures of the desktop product in its in doing what it's doing, basically. And I was just going to use them to talk about some of the systems and how we went around developing them versus the information that we have for them. So hopefully that's of a little bit of interest. If I go too deep in it, please somebody just tell me to move on. There's no problem with it at all, okay? So this is the A321neo, okay? More specifically, this is what we call an NX version, which has a slightly different cabin. Obviously, this is a Korean Air one. So one of the things that we've talked a lot so far about the system side of bits and bobs, but one of the things that I want to touch on a little bit, and I'll do so a little bit further down the line here, is the aerodynamics. You've got beautiful systems. The flight model is that other portion, as we said, and that's where the kind of making the aerodynamics work and act in an expected way can become really tricky, especially when you throw in a weather system that doesn't always give you what you need or give you anything rational. It's been crystal clear outside, out the window, and I've been stood in the sim in 10 meters worth of fog with 400-mile-an-hour winds. The expectation is that everything will still work. So you kind of get into those bounding issues where you need to try and make sure those edge cases are successfully handled. One of the really cool systems that I've spent a reasonable amount of time doing over the last 6 months is a system called dual cooling. Now, at a very top level, okay, on the engine, they're using some new materials that makes the aircraft thermodynamically different. So the aircraft will try and cool its engines in order to, or pre-cool its engine in order to stop the blades rubbing against the fan and stop the shaft bending, okay, from where it kind of thermodynamically is very different. So one of the things that I spent an inordinate amount of time doing is building the complete dual cooling system that is on the aircraft. So we do that by reference material from the manufacturer, manuals, that kind of good stuff, technical drawings. And we end up with something that is a pretty spot on representation of it. So the aircraft will calculate the system will now calculate how long it's going to take to cool the engine based on the environmental factors. So what the temperature is outside, what the pressure is, what the altitude is, and how long it's been since the engine last shut down. And actually the temperature it was when it last shut down, because those are all the items that feed into this cooling credits system. From that, the FADEC will generate a time. Hopefully, fingers crossed, somewhere between 30 and 2 minutes, 30 seconds and 2 minutes. The nifty bit about this is then both engines will spin up, and you can see it here. We've actually got an N2, so N2 is the second rotational measurement, a second stage rotational measurement of 9.7 and 9.8. And you can see these engines here. We've got 102 left on the left engine and 124 left on the right. Now, they're slightly different because the engines were shut down at slightly different times. Okay, so, sorry.
That system is the same as the Boeing rotor.
Correct. Yes. Yes, so that's actually a Pratt engine.
Oh, crap.
The LEAPs do cooling slightly differently. On the Maxes, yes, they have BRM. Yes, yeah, GTF, yeah. So the LEAPs cool slightly differently. Bow rotor motoring is the technical term for it, and it's different on the 7.3 to that it is on the 320 series. And again, from the LEAP, there's two engine manufacturers for a 321. Sorry, guys. One is called CFM International. It's a conglomerate between GE and a French company whose name I can never pronounce, and therefore I'm not going to try and butcher it whilst I'm being recorded. And Pratt & Whitney, and the other operator is Pratt & Whitney. So CFM do the LEAP engine, Pratt & Whitney do the geared turbofan. This is a geared turbofan. The cooling is roughly similar. It's just the Pratt's a lot more obvious about it, which is a nice little nuance.
In effect, though, Duncan, is that that's a separate system from the rest of the engine management system, in that it only gives you an indication of how long that engine's got to cool down when you basically landed and say, right, I don't want to turn off, do I?
Yeah, so it's actually on the start, and it will only actually display on the 320. It's one of my props from earlier. It will only actually display on the 320 when you flick the ignition switch to ignition. It takes about 10 seconds for the EIU, so the engine interface unit, to calculate how long that's going to work, and then it will display what you can see there on the engine warning display. But yes, it's essentially a hosted function within the FADEC and the EIU.
A lot of the simulation software, I presume, is systems like that, which will be independent in many ways from other things. I mean, what, is the landing gear down? Yes or no? That's just one system. And then I suppose then on top of that, you've got things that need to be integrated to give the displays, multiple displays to the pilots that might indicate more than one thing. So
yeah,
you've got a problem, you've got no tires or something like that.
Yeah, exactly. Yeah. And that is, so the way we do that communication on the aircraft is via the ARINC communication bus. We use ARINC 429. Don't know if anyone's ever come across it, but we use ARINC 429, and we've actually built a complete implementation of ARINC within our desktop environment. So we can send all the messages exactly like you would on the aircraft. It's both the good and the bad thing. It drives me slightly nutty because debugging it can be a small nightmare without the ability to actually just probe the twisted pair and see what it's doing. But you can kind of do that virtually within the so that there is kind of a common network in the implementation and a software level of that communication, of those communication buses that then feed into a system called SDAC, which is a data acquisition computer. So it swallows all the information coming off the aircraft and then decides what you need to know. So it'll either give it to the FWC, which is the flight warning computer, which will then display it here. So it generates these things here. Or it will feed it into a different display if it needs.
I'm going to ask the obvious thing there.
Yep.
Is how much AI are they intending to put into all this?
Well, It's interesting, isn't it? So that leads me back to what I was saying in terms of the lag between consumer and then into aviation with the safety mind. There is, as far as I'm aware, I don't know of any aircraft for real with any AI in any of the core functions. Thales, which is the company that make the flight management computers, are starting to look at a slightly AI-enabled electronic flight bag. Now, an electronic flight bag is essentially an iPad for the cockpit. It's a fancy word for an iPad, yeah. On there, you normally have your performance, your charts. You can send and receive some messages using the aircraft's Wi-Fi only to operational control though, and you can get the weathers and all that kind of good stuff. So there's a new generation of EFBs and flight management guidance computers that are kind of going to be slightly AI enabled, but nothing to the level that you would see with ChatGPT.
One of the discussions we've been having about AI recently here is that it seems to be developing into that there are specific systems for different subjects or different professions. You know, so there'll be a medical AI at some point in the future. You probably have to pay for it, to be honest with you. But I just think it may be that avionics or flight control or whatever that will have a distinct, separate AI. But even then, it might take 20 years to actually get accepted.
I think for that to be the case, there's got to be the trust to do it.
Yeah, I mean, I deal with some suppliers to Boeing and Airbus, and even changing anything slightly in the manufacturing process has to go through so much testing and so many test reports that it takes a year.
So very quickly before we come to the next question, small story. 777, they wanted to change the landing weight of the aircraft by £3,000. Okay, literally, in terms of the code, we're changing a 3 to a 7. No, 3 to a 6. There you go. That's why we test. So that was an 18-month affair.
Yeah.
That was a full requalification of the entire power management system of the aircraft to change that single digit. How much money pains me to think about? Tens of millions. But that's why you have such reluctance to change.
Yeah, I mean, it's great. It's great to be safe. I mean, that they can't change anything. It's really, really tied down. So it restricts the manufacture enormously, but the product is very valuable, and the order book is 15, 20 years forward. So it works out in that other way.
Yeah, it does. The biggest thing when you work in, certainly I found when I worked in the aviation sector in corporate, so to speak, was it's really easy to lose sight that actually what you're doing is affecting people's lives. It's very easy when you're in a siloed bit of work to want to just press ahead, get it done, maybe not necessarily do things to quite the depth that you maybe should, or skip a corner. You know, we've all faced it when we're under a deadline. The thing that drags it back within aviation is that actually, if you don't do it right, people can die. Hundreds of people. I'm going to come to you in just a second, if that's all right. You had a question for me, sir?
Yeah, I think it very much plays into that, to be honest, because I think there was a news story very recently about a plane self-landing in the States from a system built by Garmin.
Yes, Garmin's Autoland. Yes.
How much do these kind of plane and flight simulations actually feed back into real planes, in the sense of, I don't think Garmin self-landing system would have actually been much possible without having very, very, very accurate flight systems, or at least flight simulations beforehand, to actually know how to land a plane successfully without crashing it.
Every manufacturer will have various levels of simulators that they use for their engineering work. They can stretch from somebody on a computer in a cubicle to a full replica of the aircraft on jacks on a laboratory floor. When I was at GE, I had something kind of in the middle. I had the whole 777 electrical power system in my lab. It's kind of nifty. Lots of circuit breakers to pull, kind of tickled that one a little bit. You could pull everything and pop it in. But so that level of simulation does definitely feed into it. It's a little different from this level. It's kind of you start to get into full motion and fixed base kind of territories. Usually they're developed with the help of test pilots. So test pilots will look at the design of the aircraft, and I mean, they are far more intelligent than I am. They will come up with a way that they expect the aircraft to handle based on the modeling and the properties of the aircraft that are known. And then they will use that to develop what's called a data package. And then that feeds into your first pass of flight, kind of flight simulator results. And then once you get an aircraft to go and take flying, you could then cross-reference, and then you start to change it so it starts to react. And that's how that development cycle works. With the Garmin, they actually used a King Air as the profile aircraft for that before they had that incident that was very prevalent the other week. So they took what is already a known good in terms of a King Air 350, which is a twin-engined 10-seater commuter / business aircraft. And then they integrated over the top of that into their already established avionics suite. So
I was just thinking on the sort of aviation thing. One of the things that always hit me, I used to work for an aerospace supplier, and we just used to make the simplest little rubber washers. And we used to make them for the automotive industry, and we used to make them for the aviation industry. The automotive industries, they used to go in a cardboard box of 1,000.
Yep.
The aviation industry, small sachet, one in there, full test certificate, full information, and you have to keep the records. Anyone who's ever worked doing backups of systems, think about what this means eventually. You have to keep the records for the life of aircraft plus 25 years.
Yep.
So if you're running IT support in a business that deals in the aviation, you have to be able to restore your backups from 75, 80 years ago. I mean, we're lucky now. We only have to go back as far as computers were invented. But it's
The days of
level of
tape,
qualification is so important.
Wasn't
But
wasn't accessible.
when we then talk about things like AI is never going to exist in anything safety critical, which in aerospace is quite a lot of aerospace, until such time as you can prove why the AI made the decision it did. And current AI will not do that.
And it's, somebody was asking me at the start earlier, kind of alluded to automating cockpits away, automating pilots out of jobs. I mean, I honestly, knowing what I know and bits and bobs, I don't see that happening in my children's lifetime. Because there's got to be consumer appetite. Yeah, we can build a really fancy system that is going to fly the aircraft without any human intervention, taxi it to the gate and park up perfectly every time. We can do that. That's within our technology. Sometimes with the current state of affairs, it will go wrong. So to get it below the acceptable level of risk, which usually in aviation is 10 to the minus 22, that's going to require a lot of work. Even if you get it below that 10 to the minus 22 threshold for a regular catastrophic event, that's what would be termed a regular catastrophic event. You then got to convince the public. And I don't even think if you stood on the street and handed tickets to go to Miami for a week, you'd get many takers if you told them that you were going on a plane that was being flown completely by computer with no human supervision.
And the irony is that it's been discovered that as the computer systems get better and better and the pilots rely on them more and more, the pilots are less and less useful in a catastrophic situation.
And that is where what we do comes in, because we provide an ability to recover some of those manual skills outside of the formal work training environment. So,
yeah, for that component that we're looking at on the screen, which I'm not an aviation person. Yeah. So for that, so am I right in thinking that you had to flown? I don't know if that's the right way of describing it. From the information you could glean from the manufacturer of that, and there was no input from the.
yeah, that was 4 nights of work to get the basis in there. And Go for it.
Yeah, sorry. In terms of the back end, so is there a physics model behind that or not? Yeah. So is that one that?
Yeah, it's one I've had arms in. I didn't do it all myself because, again, not that intelligent. Because like some of the physics stuff that we do on the background to drive everything forwards in terms of desktop work is mind blowing. I look at it and it's just looks like the Matrix. It's incredible mathematics. But yes, there is a full thermodynamic model for the engines that takes into account the metal properties and all that kind of good stuff, and the outside air temperature and the pressure and heat dissipation rates and all the fun things in life. And that also feeds into that, mainly how that heat decays. So because we may have a cooling time calculated, the actual temperature, which is here, so these engines are at 40 degrees and 39 degrees because the aircraft's been sat for about 2.5, 3 hours. How that heat decays over a period of time and how the engines cool down, that's where that kind of comes in.
What do you use for your physics and like mathematical modelling? Is like a MATLAB equivalent? Or...
So yeah, some of it is done in MATLAB and out. Some of it is written in C++, which is not the nicest way of doing it, but yeah, MATLAB is used quite a lot. We use MATLAB for a lot of the flight modelling as well because the logic gating is perfect for that.
So when you're modelling a flight simulator, does the flight simulator know that it's going around a ball, or is it modelled above a flat surface? So I suppose it's kind of the difference between like Newton and Einstein.
Yeah, it knows that it's going around a ball. So it has the sim itself. So what I would term the visuals engine has a complete physics model in there as well, and then we choose to do a refined version of that separately off board in our code.
So I suppose it could go to a stupid level here as well, because obviously as you get further away from a gravitational body, time changes. Is that the sort of thing that you'd measure? Because obviously it's not significant, but although I mean it is significant for low orbit satellites. Is that something that you would counter for aircraft?
It's not something that I've yet have become a problem. Bear in mind, the A320 is going to top out at 39,800 feet. We're not into that time stretching point at that point. There's a small difference, but it's not massive. One of the things we do, however, have is we simulate all of the satellites. So we have a full GPS network built in, so the aircraft knows where the satellite should be. Yeah. So if you took a real plane, dropped at the same point in space and time, we're referencing the same satellite systems and the same satellite numbers that the real aircraft would be.
That's GPS satellites.
Yeah. So that's where we kind of keep the clocks nice and tidy using that. Poses a different. I had a really bright idea a little while ago, because this happens and I like to inflict pain upon myself. I developed a full GPS jamming model in there. So you see it around the world quite a lot at the moment, especially with aviation. There are certain areas in the world where you will lose GPS. Okay, you will lose all GPS signal or have degraded or spoofed GPS signal due to third-party actors and what they're putting out into the radio spectrum. And yeah, I had an interesting couple of days and built that, which causes issues then with clock timings because the clocks will drift. Because then there is actually within our jet a quartz model that models the quartz timing clock.
So do aircraft have that as well? They have their own quartz clock. If they lose GPS, they revert back to.
Yes, well, switched it.
The pilots.
You can't quite see it. The clock's just there.
Red screen, quartz, digital.
Well, this is actually the clock here, and you can actually. The cool thing about this is you can actually reset the time on there, and you can do it in flight if you need to. If it has drifted that far, and you can get a valid time check, you can do it.
Trust.
Cool. I'm going to bump the slides on. Is that okay with everybody?
Yeah. Cool.
Do this one. Has anybody heard of TCAS before? Some smiles, some. Yeah, cool. So TCAS stands for Traffic Collision Avoidance System. It is, you have on an aircraft what's called a transponder. Okay. That issues basically an octal. It issues a code outwards via radio frequency. The codes it issues are always octal. You just can't put a 9 in there. And TCAS will talk to another aircraft. So if you have another aircraft coming the other way and it's at the same level, your transponder and the other aircraft's transponder will talk to each other in the real world. Okay. And they will decide who's going to go up and who's going to go down. Okay. That talking is milliseconds. Okay. Now, we've implemented that in a flight simulator environment. So we have a TCAS implementation, and this is actually demonstrating something called autopilot TCAS, which is where the autopilot will fly the resolution, that up or down, automatically for you. But I thought this was kind of nifty to see. So we have another aircraft here. That's what this amber blob is. He's 700 feet above us and descending into us. Okay, we are climbing at 300 feet a minute, and we're just coming through flight level 346, so 34,600 feet. Now, we're talking in this case because we can't access their TCAS, their transponder. So we are going to give our user the safest recommendation that we can based on the trajectory of that aircraft over the last 5 seconds. So it's not a full implementation of TCAS because people get a bit weird if you just start connecting to their computer and asking whether they're going to go up or down. So we feed the user back the safest course of action. And that's one of those compromises that you kind of have to make when you're in this situation with full aircraft implementations. Go for it.
That'd be the same as whether it's AI traffic or VATSIM traffic.
Yes. Yes, yeah, exactly that. So AI is a little bit easier because you can get some data out of it. VATSIM traffic is essentially AI, just with less detail in terms of a development standpoint. Cool. The wing. This is one of the bits that I'm actually most proud of about the last kind of year or so of my work, and I know it's just a wing. So one of the things that I've done is I've rebuilt the physics model in how our wing reacts to airflow and how it reacts to turbulence. And you get something that's called wing flex. So it's that point at which you look out at the wing and it's bouncing around as you coming over the mountains or anything like that. That bouncing is termed wing flex. So the model is done in C++. It takes into kind of all of your atmospheric conditions that you would expect, and then we convert that into a bone movement on the wing. We don't use any of the native employments of that from within the visuals engine, within the simulator. We do it all off board on our own, because apparently I like to hurt myself. But it's meant that we could do some stuff in there that you wouldn't be able to get out of the simulator itself. I don't know if anyone's ever been on a jet when you've had really high frequency turbulence. So it's really bad. Like the jet you feel like you're a ping pong ball off the floor doing that, yeah? The wing will move incredibly rapidly at that point and have very sudden onsets and stops. And that's one of the things that we've been able to model using that approach, which it's a lot more lazy in the native implementation. So again, we've gated it all the way through with that kind of bad data coming out, like I mentioned earlier, just the complete mess of a weather system or the user doing something completely unexpected. Doesn't work very well when you're upside down, but then again, if you ended up upside down in the 320, life's got interesting quick.
Or you
worst
want
story,
to see what happens.
Yeah, well, to be fair, to get an A320 upside down, you've got to be in direct law, which means you've kicked out all of the protections and you've probably had some form of quite large failure. So, yeah.
I'm sure you've probably had at least a good few users who've tried.
I mean, I put a full motion sim upside down in direct law, but that's a different story and probably one that needs a beer.
Is there a kill switch for all the safety that you've developed? Is that right? We're doing it like Star Trek. We can do anything there.
In a full motion sim, yes. It's interesting, isn't it? Like full motion sims seem really benign, even when you're in them and you're doing some really interesting stuff. You're moving, but it's not that bad. One of the key reasons why, as part of every single safety brief on a full motion sim, is strap in. It's because if you push the simulator to a point where it does not know what its pitch reference plane is, it can snap to some very odd angles. And people have gone out the window because they weren't strapped in. They've gone. So it's one of those really weird things that you don't really ever consider when it comes to, okay, I'm in a full motion sim. That strap in safety brief is really important in that sense. How am I doing for time?
All right.
Yeah?
8-ish.
Ah, cool. I've kind of accidentally talked about a lot of this as we've gone through. I'm very sorry. So I'll talk about the bits I haven't. If we've got any more questions as we step through, please feel free to ask. So that is this is called a primary flight display, or a PFD, on the 7.3, and then this is the navigation display with our yogs that are very out of focus. I was trying to be arty. But this is the GDI plus drawing that we talked about earlier that is taking that ink data feed from the aircraft, from the internal kind of the internal buses, and then you're getting out your altitude and your speed on the left. You've got heading feed down here on the bottom, and then you've got your autopilot modes up here. At the moment, we're in command, so the autopilot is actually controlling the aircraft and actuating the control surfaces. Yeah, there are different levels of way you approach systems modeling. We may have noticed that I kind of tend to do right down in the weeds attempt. But there are more upper levels that you can kind of approach it at. And one of the downsides of those is, oops, if I don't throw the mouse around. One of the downsides of those is that you get to a state where you press a button and from the outside looking in, it looks like it's worked properly. Yeah. Mm-hmm. For instance, you press the generator push button on the overhead of an A320 and the generator has either engaged or disengaged. Happy days. However, if you haven't done it properly, then you haven't closed the contact that then connects the generator or disconnects the generator from the aircraft's electrical power system. So you could still be stood there staring at blank displays on the jet. So there's a very top level explanation of what I mean when I kind of come at things from a press and show message point of view to a press and, okay, the actual aircraft's going to trickle through and do everything they should do. There are a couple of switches on our desktop simulator that if you press it, it will actually take a little bit longer than we would like for the effects to be visible in front of us, because the path for the signal to get from A to B is actually so long, because we have every single wire, every single terminal block, every single resistor, capacitor that is in the aircraft is modeled within the 320 that we've built. It's a good and a bad thing. It's a nightmare to maintain. Even in terms of code, it is a nightmare to maintain, and it's a nightmare at points to debug. But you get into a lot of the nuances that you only see when you have that exact same architecture as you do on the aircraft. You see them in the simulation as well. We had a fault on a new type of fuel pump on the center tanks of one of our aircraft on the 321. It's called a jet pump. Nifty bit of kit, sounds cool, happy days. But you get fault messages out of it when you did certain things too quickly. And we were all kind of stood looking at it, scratching our heads going, why is that doing that? That makes no sense. It's implemented exactly the same way as it should be on the aircraft. Turns out, you see it on the aircraft. Airbus had to go and fix it. Again, kind of talked about this already. The ARINC buses are all timing dependent. It's very easy to miss messages if your timing gets out of whack, and that's where when you're trying to operate in a kind of real-time system on a user's computer in a flight simulator environment where you're depending on other people's code, it can become quite challenging. We do a lot of gating and checking to make sure the internal clocks of the flight simulator have changed, and changed by an amount that we would consider significant in order to run our next timing cycle within the jet. Otherwise, you end up sat there chewing data for no reason, because the outside world for the user stopped, and it just gets very messy very quickly. So timing sensitivities can be a real nuance, it can be a real pain, and thankfully, after about a year, we've finally got them all locked out, I think now, which is very pleasing. Most of our internal systems work on a base of 18 hertz in terms of how the code's going to update 18 times a second. It's good enough for what we'd like to do in the environment that we do it in. And then there are certain subsystems that either go faster or slower. So we have some systems within our flight management computer which do all of the predictions for how long it's going to take you to climb to X altitude or what your fuel is going to be at your destination. They actually only run every 3 to 6 seconds. And you see that in the box on your MUGDO when you're looking at the pages. It only actually updates every 3 to 6 seconds. Right. Any kind of questions about the sim side before I get into the last little block of this? Cool.
What sort of like prediction algorithms do you use for navigation languages?
I can't answer that because we have a member of our team who is literally the smartest person I've ever met, and he's done them all. And he is fantastic. There's something wrong, I go, thank you kindly. I don't touch those because my eyes go cross-eyed looking at them. They are some pretty incredible maths. But yeah, sorry, it's not something I can be very helpful on now. I'm much more of a power guy, I'm afraid. So
are simulators ever run without people in them? So what I mean from a unit testing kind of perspective, because I was interested with actually the 737-800, the kind of problem that it had over the last few years with the pilots were like contributing to a feedback loop.
Mm-hmm.
And I was kind of wondering whether they ever just have like flights, and then because obviously you could probably simulate a 4-hour flight in 10 seconds or what have you, and just put inputs in, either likely inputs from a pilot, and then go to the more extreme cases, what happens if a pilot does something stupid, to see what happens. Because like, for example, well, I suppose it's complicated to explain the recent problem, but it did seem like to me that would be the sort of problem that in ordinary sort of software you'd pick up that the pilots were going to find themselves trapped into that sort of feedback loop.
And that's a fantastic question. Those development simulators that I talked about, that's a lot of where you will do that type of work. You won't necessarily do it in something like that I built, or that's something you'll do on a desktop product because they just don't have the fidelity. They're really good, but they just don't have the fidelity that you need to do that level of work. I have seen cases where they don't tend to run them at quite as quickly as 4 hours and 10 seconds, but they'll run them kind of 2 or 3 times speed if they're trying to gather specific parts of data. Often what they'll do, depending on how the flight controls interact with the simulator, i.e. if you've got a yoke, so a push and a pull, or a side stick, often they will attach motors to them.
Because I was wondering whether that might be something where AI might, because like I say, you can predict what would be reasonable inputs, but then an AI system also might be able to sort of what pilots are generally doing. And I think you could train an AI model to fly realistically, or this is generally what pilots do. And then obviously you could then tweak that AI model to say, oh, this pilot is very heavy-handed with the rudder trim or the stabilizer trim, or this, this pilot, is going to do the QRA checklist for such and such an item in the right order. And I'd have thought, over like a few weeks simulating it, you could probably get a few, and obviously, you can't legislate for, complete head cases, but I thought you could, it could certainly be used to tweak procedures and, either, the checklists people use or actually the systems themselves.
Yeah, theoretically, that would be a very good use for AI if it's done in the right way. The problem is at the moment is that you don't have the rule making to let you do that. There's no, within the rules of developing systems and aircraft for aviation, there's no allowances in there at the moment to let you use AI in that manner, as far as I'm aware. It's still very much human in the loop, for good reason, because it ties us back to that. You've got to be able to explain how AI got to that point to a certain extent. So yeah, it's definitely a different approach to it that would potentially work. So
with this kind of super low level simulation of like an entire plane's holistic systems and how they all interact with each other's, Is the simulation's view of the world exactly the same as the way a plane would sit in the real world, in the sense that a lot of the physics simulation comes down to spoofing values to feed into the sensors from the standpoint of a plane?
Yeah, it can be. Depends on the quality of the outside simulator you're working with. So for instance, Prepare 3D has a really good physics model. It's not the best out there, but it's really good. There's not a lot of fakery that has to go on.
Yeah, obviously kind of more looking at the desktop simulators and kind of in the video game world, there would be optimizations you might make.
Yeah.
How does that kind of impact the more sophisticated simulators?
In terms of still within desktop?
Yeah, so
Yeah,
like if well, even in general, like if you're trying to simulate a resistor, doing that across the whole plane, I imagine would take quite a lot of compute.
It can do. So one of the things we've done is we've used threads in what I would consider a relatively intelligent manner. And it distributes the computing pretty quickly, to the point where the time it takes for the switch to energize and the circuit to energize on the aircraft is matched to what we do on a baseline computer. A baseline computer for us is not a super Camahon Dookie X3D 5090. I've just gone out and spent $8 on a computer type deal. It's representative of what the majority of the consumers that we work with have. So you can get into situations where if hardware falls below those minimum specs that we ask, where timings and the way that the aircraft behaves and reacts to certain situations can get very interesting, and not in a good way. So that is one of those downsides of the depth of simulation that we go for.
Thank you.
Yeah, pleasure. Right. World flight. Sorry, I'm not done yet. We're on the home stretch, I promise. I will try and rattle through the next couple of blocks relatively quickly. World Flight is a charity event that runs across the world, essentially. There are 16 simulators. I think it's actually 20 teams now. So 20 teams, all flying their own fixed base or full motion simulator. We have one. Our team name is Team Velocity. Over the last couple of years, well, over the last 10 years, over the last 8 years, we've raised over £50,000 for our 2 nominated charities. This year, we raised 10 grand for the Great Western Air Ambulance. And there's a little bit more details coming up. But so this is the medical director from the GWAC, the Great Western Air Ambulance. And then you've got Steve Nibbs from the BBC, because apparently I ended up doing a interview live on the 6 o'clock news at 6 o'clock on a Friday from the cockpit. Was not my best moment ever. And then, yeah, so this was whilst we were above Indonesia with full air traffic control via what's called the VATSIM network. And you can see everyone out the window as well. So if people are connected at home as well, you can see them out the window. It's kind of cool. World Flight itself consists of about 168 hours of runtime for the simulator. Okay, the sim doesn't get restarted during that. It runs all the way through, unless somebody plugs in an air fryer. Different story. We may have had a small power event this last year, which made me very sad, but it took us about 30 minutes to recover from it, so it wasn't too much of a bother. Yeah, the sim runs for about 168 hours in total. Obviously, we all know what Windows is like, so 8 machines running for that length of time without problems can be a little bit of a hope and a prayer. I said £50,000 raised for the Fight to Help and the Great Western Air Ambulance charity, and it's on the VATSIM network. So it's quite busy. We do also live stream it, which is another added layer of complexity, because we have all the video cameras within the cockpit. We have to display the chat from the live stream. There's a couple of hundred people in there watching. It's not massive, but there's people in there watching as well. They're chit-chatting away. So we have to have a way of the crew who are operating the flight talking to the people watching on the live stream, as well as talking to air traffic control. And also, if they need, they're talking back to the dispatch, which is essentially normally me located in the workshop. Put this in perspective a little bit. We do this in the 7.3. This is the route from this last year. So we started on the 1st of November, We finished on the 8th, and we flew from Sydney to Sydney via 44 other places because it seemed like a great idea. It's a lot of fun, to be fair. My team's got 16 of us. We have a giggle. We eat very well. We turn the back of the, we've got a little bit of extra space at the sim, so we turn it into a kitchen. And to be fair, we smoked a lot of ribs that week. It was great. So yeah, snake our way across the world. Now, the interesting thing about Worldfight is it's that stress test for the simulation software. It is you're not going to get a more demanding time from having a bunch of commercial pilots as well as flight simmers descend on the sim for a week and use it in anger the way that it is meant to be used and beyond a little bit. So it could become quite an engineering challenge. One of the things that I've learned over the years is that whenever we implement something new on the sim, have a backup or a way to get out of it, because something goes sideways in there when you've got 100 people watching and everyone's like, I broke it. It's really not a good feeling. So we do a lot of that now. So the level of understanding that we have to have of the sim and how everything interacts, even at a really obscure level, really does help with that fault finding on the fly, so to speak. Nice little shot of some of the team by the Great Western Airways helicopter. We did this not this year, last year. During the week, those that weren't flying went down the airbase and got to meet the crew and see where some of the money that we've raised gone. That is actually another person in another simulator on the other side of the world, parked up next to us in the 7th. That's part of that that multiplayer network on VATSIM that we were talking about. And you can just see here, we've kit the iPads out with a feed of the stream so they can see if the stream dies. Another problem you don't think you'd have in a flight simulator, and also the chat. Recently this year, we actually built a full suite of tools. Again, C#, a full suite of tools that allow us to access all of the charts, chats, messages, talk on the crew chats or on our WhatsApp group, all from those iPads in the flight deck, and be able to keep everything tidy in one place without having to open up 6 or 7 different apps and be swapping around all the time. Little quality of life things, really, which help at 3 o'clock in the morning when you haven't slept for 3 days. Another little team photo here. This is in front of us. This is kind of our reception area at the sim. Our team mascot here, his name is Zimbru. He's a German Shepherd, and he quite enjoys just curling up in a ball behind the seat in the cockpit. So I thought I'd pay the dog tax.
I mean, I'm guessing unless the seats start vibrating.
No, he loves it. Sends him to sleep. The floor shakes a little bit in there as well, and he literally just curls up on the seat behind my seat, curls up on the floor behind my seat, and just goes to sleep. He is a happy boy. He's been coming to work with me for about 8 years, so he's got a bed in there and everything. He's very happy. I do tend to refer to Worldfight as chaos engineering, mainly because it's done solely on Monster and no sleep for a week. As I said, 8 PCs, 24/7, so about 168 hours worth of runtime without any of the pre or post build up. Teams of 16 people. Everyone has a different view of how that sim's going to operate for them, and that gets us back to the user problem. The tools suite is something that we've kind of learned over the years, that more development time we put into that and how it integrates into the aircraft in terms of a simulator, it has a huge amount of benefit during the week. Allows us to diagnose faults early, allows us to isolate the faults really early and then recover systems, sometimes without even having to leave the seat. So literally, if I'm flying a sector and I see something going wrong on one of the boxes, I can restart the program, the individual program that runs that screen. I can restart the logic controller. I can restart the electrical controller if I need to. And then push comes to shove, I can restart that whole computer remotely without even having to get out of that seat. Because I'm lazy. We're nearly there. A little bit to finish up. The other thing I like to do, David said I should include something that I enjoy, so you can blame him for this. I quite like my photography.
Is that Wales?
That is North Wales. For those that know it, it is the Mac Loop. More specifically, that is CAD West. That's actually a friend of mine, a guy named Crow. That was his final flight over in the F-15E before he went off to fly the F-35 in Alaska. So I can often be found on my very rare days off. If I'm not actually flying, I'm often in the hills of North Wales with the camera. I've done some relatively cool stuff with that as well. very separate from engineering and software development and all that kind of good stuff. I've been the photo supervisor at the Royal International Air Tattoo at RAF for the last couple of years, running a team of 12 photographers across the week, delivering the output to the stakeholders. I also do a lot of work with both armies and air forces in terms of developing photographic output for them. It's been a lot of fun doing it. I've got to see some really cool things. A couple of photos from that coming up. This is a Belgian F-16 leaving Fairford. We call this an office shot. I rarely get them because I normally can't pan quick enough.
Still on the wing there.
He is. I'm actually at the top of a grandstand, and he is like that as he comes past. That's one of my favourites. This was a night shoot with the 2nd Royal Anglian Regiment in Wales. One of those time pressure situations where they had 40 rounds left for the Gympie, and I had about 4 seconds to frame and take the photo whilst it all came together, whilst being on night vision goggles. So that got entered into competitions and bits and bobs for the army, which was kind of cool. This one actually won an award, won a competition for the army as well. But this is a mortar firing on Salisbury Plain, where the mortars
Actually went over your head, didn't it?
maybe. We won't talk about that. But yeah, that was probably one of my highlights of photos from last year. And then this is another real image. It's a Ukrainian Su-27 tank. That the sky is my favourite sky in that.
Russian built.
It's a Russian built, Ukrainian operated. Cost me 3 crates of beer to get the crew to leave the covers off it overnight. But we got some really good photos. That was a nice little evening jaunt. And then 2 slides. This and the next is my goodbye slide. So that's actually me in the elephant head. We do stupid things for photos. I really wish I hadn't done that on a 34-degree day, because we all know what tarmac gets like when it's warm. I was mildly toasty, but that's for the Canadian C-17 because an elephant is their mascot. So I actually ended up marshalling the aircraft in and parking it. One of the more random things that I've done. And there you go. So thank you so much for listening to me ramble.
Rambled, and it's been absolutely good.
Hopefully it was useful.